Next, we see that Dalton's law of partial pressures tells us how to deal with a mixture of gases. So if we have 3 cylinders of gas and they all have the same volume, one has a pressure of 300 kilopascals, one 600 kilopascals, and one 450 kilopascals, simply the sum of these 3 numbers is going to be the pressure of all 3 gases in the same container when combined. A more typical way of applying this law is to think of a mixture of gases and then consider each individual component's partial pressure as a concentration of that gas in the sum of the whole. When dealing with partial pressure, we deal with the concept of mole fraction, which you should remember from last quarter. And a mole fraction is simply the moles of a particular component divided by the total moles of gas. So let's do some problems. First, at 25 degrees Celsius, we have a 10-liter vessel that is filled with 5 atmospheres of gas A and 7.89 atmospheres of gas B. What is the mole fraction of gas B? Now, for each question in this video, I would like you to pause and try to find the solution on your own first before watching me do the solution. Pause now. To solve this, we note that the total pressure is the sum of the partial pressures. So, since we have the same 10-liter vessel with 5 atmospheres of one gas and 7.89 atmospheres of another gas, the sum of these two is 12.89 atmospheres. And so the mole fraction of B is going to be the partial pressure of gas B, 7.89 atmospheres, divided by 12.89 atmospheres, or 0.612 atmospheres. Sorry, this should actually be unitless because a mole fraction is unitless. Note that we're given 3 significant digits in the problem, and although we only have 2 significant digits after addition, because we are dividing, we should have 3 significant digits in our answer, because the value with the least number of significant digits is 3. I should point out that problems, like the ones I'm going to show you, are all in the homework that is due on Thursday. So let's do another. A chamber contains equal molar volumes of carbon monoxide, carbon dioxide, nitrogen, and oxygen. If the total chamber pressure is 3 atmospheres, then the partial pressure of carbon dioxide is what? In this problem, since the molar amounts are equal, and we have 4 different gases, then each of these gases has a mole fraction of 1/4. And so since we are interested in the mole fraction for CO2, CO2 will be 1/4, and then the partial pressure of carbon dioxide is therefore 1/4 times 3 atmospheres, or 0.750 atmospheres. Once again, we have 3 significant digits in the value that we are given, and therefore we have 3 significant digits in our answer, because we've carried out a multiplication operation. Let's look at 2 more. At 55 degrees Celsius, a 16-liter vessel is filled with 8.25 moles of gas A and 8 moles of gas B. What is the total pressure? In this case, we sum 8.25. Here we go, try this again. In this case, we sum 8.25 moles and 8.00 moles to get 16.25 moles of gas total. And then we use the ideal gas law to solve for total pressure. And so I'm going to rearrange it in my head here as P equals nRT over V. And this is simply 16.25 moles times the ideal gas law constant, 602 liters atmospheres per mole Kelvin, times our temperature, which is 55 degrees plus 273.15 Kelvin over 16 liters. And when we calculate that out, we get 27.3 atmospheres. For our final question, we have a mixture of gases that contains 0.31 moles of CH4, 0.25 moles of C2H6, and 0.29 moles of C3H8. The total pressure is 1.5 atmospheres. So let's calculate the partial pressures for each gas. In this case, once again, we sum the moles so that we can calculate the total and then use that to calculate the mole fraction for each gaseous species. And the sum here is 0.85 moles. And then for each species, we calculate 0.31 moles of CH4 over the total, 0.85 moles. Once we have the mole fraction, we need to multiply by the total pressure, because this is a fraction of the total pressure. And so for methane, our fraction of the total pressure is 0.55 atmospheres. And so the partial pressure, or concentration, of CH4 in this mixture is 0.55 atmospheres. Likewise, we can do a similar calculation for C2H6. So for C2H6, we have 0.25 moles of C2H6 divided by 0.85 moles total times 1.50 atmospheres, our total pressure, and I get 0.44 atmospheres is the partial pressure of C2H6 in this mixture. Finally, we can calculate that we have 0.29 moles of C3H8 and a total of 0.85 moles of gas. And since the total pressure of all this gas is 1.50 atmospheres, multiply it and find that the final concentration or partial pressure of C3H8 is 0.15 atmospheres. And if I add these up, they should add up to 1.5. 0.55, 0.44, that's 0.99, and then 0.51, that is exactly 1.5 atmospheres. Done! I hope this clarifies how to approach questions of partial pressure in mole fraction with ideal gases.